Welcome to another installment of the Robinson Twins present The Earth is Our Spherical Home Planet. In this installment, we address this issue where some people can't seem to understand how, if the Earth is a sphere and it's spinning, why aren't all the ocean's waters thrown off into space? How could a spinning ball hold water? So we have memes from flat earthers who say water doesn't stick to a spinning wet ball. Well, we're going to debunk that idea and support the idea that water actually can stick to a spinning wet ball right now. First, let me react to this flat earth meme that tries to debunk the spherical earth that rotates. Spin a ball that has water on it and the water always flies off. Well, not all of it. But not this spinning ball. The earth is 71% water on the surface. Yet water magically sticks to it because of a theory known as gravity. Well, theory in science is not magic. It's very well supported scientific proof. So, since they used the tennis ball for their meme, we're going to use the tennis ball and show just how much could actually stick to a tennis ball when it's spinning. And then compare that to how much water is on the Earth. So here are the parameters of the experiment. Okay, so here are the parameters and measurements I got from my spinning a wet tennis ball experiment. I took the tennis ball and a scale, one from my kitchen that can go down to zero 0.1 grams, and I weighed the tennis ball dry. It was 57.6 grams. Then I put it under the faucet and let it soak in water. Made it, whatever water could run off, allowed that to happen. I put it on the scale to weigh it with the water. I got a reading, but then when I picked it up, I saw there's still a little puddle on the scale. So I went ahead and wiped that clear and weighed it again. And I got 61.9 grams. So the difference is 4.3 grams. That's how much water was actually on this, holding the tennis ball was able to hold on it. Now, grams of water at room temperature, 20 degrees Celsius or 68 Fahrenheit approximately, can give you also the cubic centimeters of water because the volume in the metric system is based on water already. So I took the tennis ball, I measured it for another video, and found its circumference at 21.5 centimeters, and using a formula to define the surface area of the tennis ball, which I won't show in this video. You can look that up yourself. I found the surface area at 147.1 square centimeters. So I took the 4.3 cubic centimeters and divided by 147.1 square centimeters to see how thick the water would be if it was evenly distributed around the ball, the sphere, how thick it would be. And that came out to 0.0292 centimeters of thickness. That's pretty thin, but it's measurable. So then I decided to compare this tennis ball to how thick the water would be on the Earth. Our Earth has an estimated volume of 1.4 billion cubic kilometers of water on its surface. The surface area of the Earth is 510 million square kilometers. Do the same division for the Earth that I did for the tennis ball, and I get 1.4 billion cubic kilometers divided by 510 million square kilometers, and I get 2.745 kilometers of thickness. So if the Earth was a perfect sphere and the water evenly covered it, it would be about 2.745 kilometers thick. That's more than a mile and a half. So now I wanted to compare the thickness between the two, the tennis ball, how much water it could hold versus the Earth. Okay, so I took how thick the water was on the tennis ball and divide it by the radius of the tennis ball. So I get 0.0292 centimeters for the water's thickness on the tennis ball on the surface. Divided by the radius of the tennis ball, 3.42 centimeters, and I get 0.00853. That's the proportion of water thickness to the radius of the tennis ball. To do the same calculation for the Earth, we get 2.745 kilometers is the thickness of the water on the surface of the Earth. Divide by the Earth's radius, 6,371 kilometers, and I get 0.00043. And if you divide the tennis ball's proportional number by the Earth's proportional number, you get a ratio of 19.8. So that means this tennis ball was holding 19.8 times thicker amount of water on its surface than the Earth does. So here's the experiment. A wet tennis ball on a rotating platform that will complete one rotation in about a minute. I'll leave the experiment running in the corner while I discuss the results of this experiment. The next thing I looked at was the rotational speed. I put the tennis ball on my platform here and measured its rotation. It can rotate about once per minute, but I was going a little slower than that, so I had to make an adjustment. I watched the video and saw that it took a little over a minute to rotate. It took 7 seconds more than a minute. So that was 67 seconds. So I'm going to figure out the rotational speed. 67 seconds per rotation divided by 60 seconds per minute gives me the answer of 0.896 rotations per minute. So it's a little less than one rotation per minute. Now there are 24 hours in a day, 60 minutes in an hour. You multiply those together, you get 1,440 minutes per day. You take this rotational speed that I got from my little platform and the tennis ball, and you'll discover that compared to the Earth, this rotation was 1,290 times that of the Earth. It was spinning, even though it didn't look very fast, it was 1,290 rotations in a day, where the Earth only rotates once. So my conclusion is, from the tennis ball spinning 1,290 times faster than the Earth spins, and that, however, there was no water flying off of it, even at this high rate of rotation. So I can conclude that water can stick to a spinning ball. It's confirmed. So we've confirmed that because of the effect of gravity holding water to the Earth's surface, that even with its rotating, the water will stay on it. So the spherical rotating planet Earth that is our home will hold all the water just fine. If you like this kind of content, be sure to like and subscribe and hit the notification bell. We'll see you in the next one.